So, good morning. I would like to thank the organizers for inviting me. It's great to be outside the EU now. Very nice, very refreshing. I have to admit that Tilburg University, that I'm affiliated with, you can see that here, hopefully, well, here, is now indeed in the top 200, but it's on place 198. So, it's the worst university of the Netherlands for the moment. But we're working on it. And I'm also affiliated with Den Bosch. Hertogenbosch is a city that is famous for the painter Jeroen Bosch, or Hieronymus Bosch. And there I'm affiliated with the Data Science Center. And we're hiring teachers. So if you have teachers available on data science, I'm interested. Today I will talk about social agents, or the future of artificial intelligence and computers. How do we make computers more human-like, that they understand us, that they understand our facial expressions? And in my domain, this is known as effective computing or social signal processing. And I will focus specifically on the automatic analysis of facial expressions. And this has always been something that was in the domain of psychologists and not in the domain of computer science or AI. But now the big companies, Apple, Microsoft, Google, are focusing on these kind of things because they are important for the next generation of computers. And it's actually quite interesting because the traditional way of how we look at intelligence and how we consider intelligence is in terms of problem solving and what is known as high-level cognition. So people that are very well, that excel in chess or in mathematics, they're very intelligent. But we also know something about social intelligence. And maybe the social intelligence is much more important. So this high level of cognition is traditionally associated with our frontal cortex, so planning and making sure that you think ahead in time. But actually there's a well-known hypothesis, the so-called social brain hypothesis, that explains that it might be very well that our mental capacities evolved because we had to deal with other people. And we had to make social inferences about what other people would do, whether they would kill us or would help us, which is quite important for survival. And also in scientific communities, this is very important. So this social interaction and making social inferences about other people is much more important than for the development of intelligence that many people realize. So, and this means that we can learn from that if we want to develop intelligent agents. And in terms of the intelligent agents, you can think about robots or virtual agents on a screen that we communicate with. And of course, we don't have that yet. And we don't know the detailed dynamics of nonverbal communication. And this is, if you talk to people, so in the break, for instance, if you talk to somebody else, there's a lot happening in your voice and in your face. And there is something known about it, but now, thanks to technology, we can have a more deep analysis of what is happening there. And this happens in the field of social signal processing. Let us start by looking at the face. We all know the face, and I show you a famous face to start with. Do you recognize this face? Who have seen this face before? Nobody? This is a very famous face. So I'm now showing you this face, and at the beginning it might seem a bit odd, this face, but there's some familiarity. I guess most of you are familiar with this picture, but of course the face is a bit distorted. And what happens if we see a face like this, then in the beginning we think, oh, that's strange. But after a while we adapt to it. And in controlled experimental circumstances, if you present participants in the experiment with this picture, for a minute or so, and then show these two pictures and ask people, what is the real Mona Lisa? Then they will say, the enlarged one is the real one, because their reference of what is a face is shifted a bit. So we are adaptive, and we are very sensitive to the configuration of faces. And actually, this is already known. There's a famous researcher called Paul Ekman in the United States who developed a taxonomy of facial expressions. So these facial expressions, here depicted by one of my PhD agents, students, shows that you have different ways of changing your face. And although these might be very subtle, they have an important signaling function in social communication. So you can see, you can infer from his facial expressions what he is thinking or what his intentions are. And we would be interested to have computers recognizing these kind of patterns And we are helped by this framework called the Facial Action Coding System of Paul Ekman, which is a kind of knowledge-based basis, mathematical basis for coding facial expressions. And this is an old picture of his work and, that talks about the building blocks of facial expressions. And the taxonomy is, for instance, action unit 1 is that, that you raise your eyebrows, for instance. That is one of the building blocks of facial expressions. By the way, the work of Paul Ekman featured in a TV show called Lie to Me, that some of you might have seen, where the main character was helping the police with inferring whether criminals were lying or not. And, but it was also referring to these action unit coding. So what we can now do with all kinds of advanced software techniques is do this automatic coding automatically, or this facial encoding automatically. They used to be training individuals to recognize that from videos, but now we can do it with computers. And we can do that in almost real time. And to show you one example of a study that we did, actually it was a study prompted by a news broadcaster in the Netherlands. They said, can you use this technique to detect deception in humans? I said, well, detection of deception is impossible to do with a computer, but at least we can see what signs there are in a face, like the face of Lance Armstrong, when he is lying about his doping use, because we have a lot of footage from TV interviews where he's lying about the use of doping. And we had fragments where he was speaking the truth about his illness, and fragments where he, in hindsight, was clearly lying about his use of doping. So, and these fragments show were interviews like this one, where he is, you see the Dutch subtitles here, but that's not important. But here he is kind of telling the interviewer that he is not using doping. And it's a kind of act he's using all the time. And we asked people to look at these videos and to tell us whether they could recognize whether he was speaking the truth or was lying. And of course, without the subtitles, we only showed the face. And people were very bad at this. And that's because they don't know where to look. But of course, we can train computers to recognize the facial expressions that are associated with the deceptive intentions of him. And it was very easy to predict it. So we found on using only facial expressions, we were well above chance level. Even vocal expressions held there. He had a kind of, the pitch of the voice was slightly higher for the deceptive part of the interview. And if we looked at action unit 4, which I will show in a moment, is one particular building block, that was the best predictor of whether he was decepting or not. Again, it's important to emphasize this is not deception detection, it's recognizing in TV interviews when Lance Armstrong was deceiving the interviewer in that situation. It might be that if he lies to his wife at home, that he has a totally different act. But the point, that's not the point, it's not a deception, it's that these computers are very sensitive to these very subtle signals. And here you see action unit 4, and that's actually referring to these parallel stripes here, these vertical stripes. And that's what you see in all the interviews where he was lying about his use of doping. And the nice thing is that we have this sensitive computer that has no knowledge of human context and is, in that respect, humans excel, of course, but it's much better than humans in just looking without any context at what happens in the face. Now, of course, if we want to build future generations of computers, which are faces on a screen that look at us and interact with us, then facial interaction is important. Well, we studied these facial interaction dynamics in dyadic interactions, and our underlying assumption is that if you talk to somebody, then you can describe it as a dynamical system. So you have the dynamics of your face, which are generated by the facial muscles that are the basis of this Ekman system of facial action units. That's one dynamical system. Then you have the dynamical system of the other person to which you are talking, to whom you are talking. And then the interaction. So the interaction is a dynamical system composed of two subsystems. And it's known that in a good conversation, if you have a match with a person, then there's a coupling. There could be synchrony, so that if you raise your eyebrow, your partner is also raising the eyebrow. Or there could be a vocal mimicry. And mimicry can even be delayed in time. And we know this is true for human-human communication, but we were interested, is this also true for human non-human or virtual human communication. So we did the following experiment. We worked together with Eindhoven Technical University, and in Eindhoven they have a smart home where you have a kitchen and you have all kinds of sensors in the kitchen. And we showed this person to people in the house when they were were tapping water. And when they let the water tap on for too long or too much hot water, this lady here changed from a neutral expression to a kind of, well, a bit angry expression. And if you were very sparse with use of water, she smiled a bit. And this works. It's unbelievable. It's a social signal that works. So you can manipulate humans by very subtle signals of an avatar that you even don't have to attend to this person. But what is very important is that this avatar is following you. So if you walk by, you see the face moving, and it gives a very strong feeling that somebody is watching you, which is not always very pleasant. But in our controlled experiment, we did the following. We confronted students with a situation where they were looking at an avatar. And this avatar was animated, so the avatar could talk. And we manipulated two things, the facial expression of the avatar and the vocal expression of the avatar. So we changed the facial expression in terms of happy or sad, and the vocal manipulation was the pitch of the voice. And the students were engaged in a task they had to repeat or associate with words that the avatar expressed. What is important, and that's why we use this device, is that we had full visual access to the face of the student. So we could measure the facial expressions and, of course, also the vocal expressions. So these expressions that we visually manipulated in the avatar were these emotional expressions. And we also did some auditory manipulation. And the idea was to see if we could see an effect of this manipulation. And without going too much into details, we found effects, for instance, for happiness, that these kinds show for female students and male students. In general, female students are more inclined to show this mimicry. That if the avatar had a very subtle smile or showed a very subtle happiness, especially the female students had a tendency to mimic that. We had a few male students that had kept neutral all the time. I think they were just sleepy or something. But in general, the general pattern is that you see after some delay, about 1 second, you see a peak in the mimicry of the facial expressions. Students are not aware of that. We are not aware of that. But this indicates that there's a kind of bond between the virtual agent and the human. And we saw a similar thing in the vocal expressions. So it's a subtle but very robust effect. So the point is that this shows that there is a kind of bond. It's possible to create a kind of human-like bond between a virtual agent and a human person. But what we're not clear, because we use correlation as a measure, we're not sure what the causal relation is, because correlation is only showing, and of course there was a delay, and if there's a delay, it's quite likely that the person is following the avatar. But we would like to bring this a bit further, and in our second experiment we looked at this dynamic coupling idea. And to explain this, I have to go a bit into the detail of dynamical systems. So in a good dyadic conversation, facial dynamics are coupled. That's the basic assumption that we have, and this is backed up by psychological evidence. This coupled system forms one dynamical system. And this means that we can measure the causal coupling. So if you talk to somebody, are you following this person or is this person following you? In terms of facial expressions. We can now measure that, and for that purpose we use a technique called convergent cross-mapping. That's a technique from linear systems or dynamical systems theory that is, for instance, used in climate studies to see if certain certain phenomena affect the climate. And you might be familiar with the Lorenz butterfly. This is a story that the weather system is such a complex nonlinear dynamical system that if a butterfly flaps its wings, this could have long-ranging effects on thunderstorms elsewhere in the world. This is all based on a mathematical formulation of a climate model known as the Lorenz Attractor. And I don't want to intimidate you with equations. The main thing to take home here is that we have 3 variables in this system. And they're all coupled, so you have x, y, z, and x depends on y y depends on z and y itself, and z depends on y and z. So this is a coupled system. It's not independent. And this is the well-known chaotic Lorenz Attractor, which shows the dynamics of this system. And now imagine that this is a model of what is happening in this situation. We have two phases. The dynamics of two phases are coupled, and the interaction between these phases can be seen as an attractor, as a chaotic or non-chaotic attractor. And the nice thing is that according to a famous theorem in chaos theory, the so-called reconstruction theorem, which I will explain in terms of these phases, if I have two persons interacting with each other, like you will do in the break, then I can watch one person, and looking at the facial expression of one person, I can predict what happens in the other face if that person is leading in the conversation. If the causal relation is reversed, then the other person is a better predictor of what happens in the other phase. So that's the basic idea. And this idea is actually at the heart of this technique, where you can say, okay, if we have one phase, then this is called a shadow attractor. You kind of reconstruct the attractor associated with the interaction by looking at one phase only. Then you get something like this. You can do that with the Lorenz equations. You can do it with the other phase. And now you have these two, what are called shadow attractors, which are reflections of the overall attractor. You can apply convergent cross-mapping. And this is a technique that there's a nice video that actually illustrates what is being done in this technique. So here you see the original full-fledged manifold of the attractor, of the Lorenz equation. This is, let's say, the interaction between the two phases in my metaphor. And this is one of the phases. And you see there's a direct coupling, of course, because this is a reconstruction of the original interaction. So now we have one phase. This is the interaction between phases x and y. And this is the other phase, phase y. And now we have a direct coupling to the interacting system, but we also have both subsystems which are interconnected. And now the funny thing is, if you are following the dynamics of phase x, you have information about the underlying interaction, and you might be able to predict what is happening in the other phase. That's actually what I just said before. One phase can be used, the facial expression of one phase can be used to predict the facial expression of the other phase. Well, this convergent cross-mapping is actually formalizing that, and it allows you to measure the causal coupling between two time series, if the underlying system is coupled. Well, the assumption is that if two people have a conversation and they are listening and looking at each other, you have this coupled system, and you are able to make these kind of predictions and to make these kind of measurements. Well, we did that, for instance, with an action unit 12, which is this action unit, a very subtle smile. So we were tracking the dynamics of facial expressions whenever they were smiling, of people interacting. So we used the same setup that was used with this avatar, but now we used two of these setups. On each side of the setup there was a person. They were interacting with each other through the screens, and at the same time we had full access to their facial expressions. We measured them, in this case action unit 12, and we had 6 pairs of students that we measured. And we looked at, we had female-female compositions and female-male interactions, and we asked them about the evaluation of the conversation. And this is a typical result that we got. So here you see participant 1 of the pair and participant 2. And the vertical axis indicates the correlation of one facial expression with the other. So how much does one face predict the other one? And what you can see from this interaction is that the green participant of the dyad, of the interaction, is has a larger control on the face of the other than the second one, because it is a larger value. So if you take the face of participant 1, you can better predict what the other face is doing than when you take the face of participant 2. So this gives you access to what is happening in these facial interactions. And this shows for the 6 dyads the different configurations. So you see sometimes the blue bar is larger, which means that the first is leading. And sometimes the green bar is larger, which means that the second participant is leading. And these are all different dyads. So what we can conclude from these experiments is that these causal coupling strengths can be determined. We have now a model of the dynamics of facial expressions. And what we're now doing in our labs is we are creating an avatar that is fulfilling the part of one participant in these dyads. So we are creating a virtual avatar that is performing in a dynamical way with facial expressions that look like human expressions. And this is the way we're now trying to do that. But the idea is that we can also manipulate and measure at the same time the quality of the conversation by doing this. Well, what are the implications of future agents? Future artificial agents should be capable of generating and recognizing these social signals. Well, we focus on facial expressions. We now look at superficial signals, but in the next stage we will also make deeper inferences. And we already see some of these techniques coming, like Amazon Echo, which is a voice-based agent. But where we actually want to move to is what we already know from the movie of Harry Potter. So those of you who saw these movies, there is this scene where they walk in this castle and they enter a room where they have to talk to the fat lady on a painting. Well, this painting, that's actually the picture you should have of our future interfaces, that we have in our homes and our buildings, we have these screens, and your personal agent welcomes you and recognizes whether you're stressed, whether you're happy, and will have a conversation with you. But it will take, I think, 10 to 20 years. Thank you very much.